Okay, so as I said, we have to, I wanted to write the Lagrangian for the field, right? We wrote the Lagrangian for the interaction of the charged particle with the electromagnetic field, but of course you can also write a Lagrangian for the fields themselves. So I write it here in this form, and then we discuss it. So you see, you take the square of the field strengths, F, and like this. That's you can compute this quantity. You see, is a scalar, right? The Lagrangian is a scalar because you see all the indices are saturated, and in fact, it's a nice exercise for you to compute this quantity. So you take two matrices, the two matrices that we define for the field strength tensor, F alpha beta, with the E field and the magnetic field, and you take this sort of contraction of both. And you will see this is essentially is the E field square minus the B field square. Okay, so it's not the energy; is something is the difference between these two densities. But anyway, this is the Lagrangian. So what I say, if you compute this quantity, you will find something like this, proportional to this difference. Okay. So you see that is a scalar. So the only thing is that what are the Lagrange equations in this case? You see, as I said last time, we are used to think of generalized coordinates, and what are the generalized coordinates in this case? Well, they are not. They become fields, right? So they are components of the. If you have a field with many components, I don't know, components. But the point is that it's not a coordinate, it's a field now. So it's a variable with different values at different points in space, time, in fact. Okay. And similarly, where we had the generalized, so these were the generalized coordinates, and now we had the generalized velocity, this is replaced with the derivatives of these fields. So, of course, one should do this carefully, but we don't have time, and this is part of this different. Probably, I don't know if you have advanced quantum mechanics, maybe. Yeah, you do have. I saw next. I'm not sure what you do in that class, but maybe you will do something like this. But the point is that you see that we wrote the Lagrangian was what? Was a sum. If you had the Lagrangian many particles, was the sum of the Lagrangians of each particle, right? And this, you understand that because it's not any longer, as I said, a numerable number of coordinates, but you have an infinite larger number that is a continuum of so to speak, coordinates, the Lagrangian becomes an integral of this Lagrangian that is a function of these fields. Okay? So really it's not the Lagrangian that you put here, it's called a density of Lagrangian, and so this I should be more precise and say this is the Lagrangian density for the field, okay? Then when you integrate over the volume, you get what you call the Lagrangian. So by analogy, where we had the Lagrange equations that I hope you still remember, it was just this, right? You see that the generalization, if you look at this, is a sort of a translation table, is just going to be some derivative, right? You see, it's in a way covariant because you don't take just the time derivative, and these are the momenta. Okay. So for the case of the electromagnetic field, these field variables are going to be your 4 potentials, okay? So in other words, this equation becomes, I write it here, you take the Lagrangian density that I wrote, and you take a derivative, right, you take the derivative of Lagrangian with respect to the derivative of the vector potential. So that is this part. Then you take this derivative, and then you put that equal to the other derivative. And how do you extract this? But you just have to rewrite. Remember that f alpha beta is by definition d alpha d beta minus d beta d alpha. So and then you have, well, actually this is downstairs. And this is upstairs. Minus 1 over c j alpha a alpha. So here you have explicitly the dependence of your Lagrangian density on this variable, so that if you do the computation, you find that this is 1 minus 4 pi f alpha, f beta alpha, if you wrote alpha beta. I'm sorry, beta alpha, then beta alpha, if you write here beta alpha. Notice that it makes a difference if this index is a lower index or upper index, right? That's why you should be careful because of the Minkowski metric, at least for the 0 component, that if it goes up, it gets a minus, right? Because you lower and rise indices by using, so what I'm saying, alpha is equal alpha beta, right? So you lower the index by multiplying by the Minkowski tensor. But because this is always true, but because in 4 dimensions, so you see that the 0 component, right, will be this. Therefore, this is minus a0. So that's why it's important to remember where these indices are. But okay, this is just a footnote. And this is 1 over 4 pi. This is a completely antisymmetric tensor, right? So it's alpha beta. And what is the other part here? The other part is the derivative of the Lagrangian density with respect to the field that you are using as a coordinate, a generalized coordinate that I said is the alpha, right? So again, by inspection, you see here is only momenta in a way, so you get only this term here, minus 1 over c j alpha. And then you have to take this derivative here, right, d beta, so you take d beta here, so you have d beta. So you see that when you pull these two together, you get 1 over 4 pi d beta f actually I like it this form, beta alpha equal 1 over c j alpha. That if you remember, if you take the 4 pi on the other side, this is exactly the first set of Maxwell equations, okay? So indeed, this is the Lagrangian that you are supposed to use, and therefore, this plus the Lagrangian that we wrote on Wednesday is the Lagrangian for the electromagnetic field, and then you can proceed as we did for mechanics by writing all the well, you write the equations and then you solve them. Then you are back to in this. So the last ingredient, if you wish, and then I stop, is the what is called the energy momentum tensor. Okay, so you can define a tensor that is, so you take the Lagrangian density for the electromagnetic, so electromagnetic quantity. So we said is d alpha a, I guess, lambda, d beta a lambda minus eta alpha beta. This is the Minkowski tensor L. So what is this quantity? This is the energy momentum tensor in space-time for the electromagnetic field. So this is it contains the same information that you have, say, for a particle, is the generalization of the form momentum for the particle. And in fact, if you plug in the Lagrangian that we wrote, that I wrote one blackboard ago, you get 1 over 4 pi f mu alpha f nu alpha minus 1/4 eta so here I should switch, should switch the indices really. So alpha beta mu then alpha beta f mu nu f mu nu. Okay, so alpha beta alpha beta alpha beta. And if you look now at the single component, for instance, the 0, 0, the time component of this object, so that means you replace in here 0, 0, and 0, 0, you will see that this quantity is 1 over 8 pi e square plus b square. So take these components, do this computation. That's again a useful exercise if you have time. Plus something that is just a derivative. So it's the divergence of phi e, so a weird object. But you see that when you take so this is a energy momentum tensor density, you see. So if you integrate this quantity, you take the volume integral of the T00 component. So this is just it's a total derivative in a way, right? So if you it gives no contribution when you do the integration. And here you have just 1 over 8 pi, the integral over the volume of this. But this you should recognize that is the energy, right? Because this was this is the energy density. So if I integrate over a certain volume, I get the energy. So this is the energy of the field. So you see, the time components of this object is what we call the energy of the field. And probably you can guess what this is going to be, the time-space component of this object. When you integrate over a volume, again, is going to be 1 over 4 pi if you E cross B, this integral. So this is like the momentum, right? It's the Poynting vector. So this, just let me finish. So this tensor puts together the same way the form momentum of a particle accounts in space-time for the energy and the three-dimensional moment of the particle. This is a sort of the analogous concept for a field, and you see that then the 0 component is the energy, the 0I component is this, and the ij components are those complicated things that I wrote when we were doing the this computation in three-dimensional space. Was the rest that I call. Everything that was not this were those parts that are called the stress tensor of the field, okay? That is the space-space component. Yes? What? Hello? You went power saving. Yes? What? This. Alpha, beta, mu, nu, mu, nu. mu, nu, well, anything you can call it. You saturate these indices, right? So this is the trace. Hmm? Well, it's the usual thing. If you have alpha, beta here, you must have alpha, beta, alpha, beta. The rest must be saturated, right? I mean, repeated index means that is sum, right? You see why this Einstein convention is useful as you have many indices. Okay, so this was what I didn't have time to finish on Wednesday, and so I think you have all the definitions for discussing the electromagnetic field in space-time. Okay. And so, as a final exercise, I want to rederive with you this is a sort of a central problem of electrodynamics, that is the fields generated by, well, I want to solve Maxwell equations first, and then maybe, if we have time, specialize this solution that is going to be manifestly covariant, okay, for the case of the moving charge particle. So we rederive one more time the linear Vickers potentials and maybe some of the radiation. But let's see how. Probably I won't have time to do that. But so I just wrote there the Maxwell equation, right? This. The other set is just a constraint, right? You understand. So the dynamical one is this, because this tells you how, for a given charge density and current density, you can compute the electromagnetic fields. So instead of doing what we did a few weeks ago and solve the Maxwell equations by components, we may just solve those directly, right? Why not? We are in space-time. And the way to do, actually, instead of solving we do the same that we did back then. So we introduce the four potential, right? And you remember that the equation satisfied by the four potential is that is this, okay? So this square is d alpha in 4 dimensions. So this thing is something like d2 dx naught square, so the time component, minus or like this, depending on the signature. So this is the Laplacian, and usually this square is called the D'Alembertian. But this is the same of this. Minus d here. No, I think. And in fact, this term here, you see, this is the sort of, you remember what? This is like the Lorentz gauge, right? Written in the covariant form. You remember the Lorentz gauge was this, the gradient phi plus the time derivative, but this is all included in this d alpha. So let's go to the Lorentz gauge, so that this equation becomes the simpler one. That is, in fact, this. And actually, we want to solve this equation. So it looks like what we did in three dimensions. It's just in 4 dimensions. But we proceed in the same way that to solve this equation, I actually solve a simpler equation first, that I look for the green function for this equation. And what is the green function? Is if you take this derivative at a certain point in space, x, then the green function for this problem, right, is the one that when you apply this operator to your green function, you get the famous delta Dirac delta function. And it's just like we had before, but now it's the full 4-dimensional delta function. So is that is a dx, right? D x vector minus x naught vector. Sorry, x prime vector. Where this is time and this is the 3 spatial coordinates. Okay, so this is the 4-dimensional delta function or Dirac function. In fact, you see that it can only depend on this difference, so you may as well introduce the the space-time coordinate z alpha to be this difference here. So that saves us some work. That means I can write this as dz equal d4z. Now, if I do the Fourier transform, you remember, or maybe not, because, well, I hope you still remember, we did the Fourier transform of this, but we did it in 3 dimensions, right? And then we left the time component sort of around. But now that you learn all this space-time formalism, you see that I can define my 4-dimensional Fourier transform to be, you take a 2 pi now to the 4th, and then you Fourier transform, so you go in the k space, right, by Fourier transforming the dz e to the minus kz. Ah? No, I mean, well, I mean, it's a convention, but look, my convention is that you have as many 2 pi as dimensions of space. So we had 3 the other time, and we have 4. But of course, you can do. According to this definition, you see that the delta function, right? You see the delta 4 of z, right, is just 1 over 2 pi 4 d4 k e to the minus a k z dot. So I guess if this is the definition, then I should do it like this, right, to be consistent. So this is the Fourier transform. So this is in the k space. This is in the space-time, if this is the definition. But you can notice that this k dot z is in 4 dimensions, okay? So you have k dot z dot. And I think that here, to be consistent, I have to take the other metric, okay? You see, I took the other metric, is the metric that is plus, minus, minus, minus. That's good exercise to switch metrics. Do you understand what I said, or it just? I mean, this thing is all. This is k alpha z alpha, right? So that means that is eta alpha beta k alpha zeta beta. So what sign you get for the 0, 0 component, it depends on your metric. So here I took this metric here, the one I said never to use. Okay. Just to be consistent, I immediately use it. But okay, but it's important that you understand this is just, as long as in your computation you stick to the same metric, it's like the normalization. I mean, you can put here 1, but then you have to remember that you had this 2 pi. Anyway, clearly, if I do the Fourier transform here, right, you see that this operator just gives me minus k dot k, right? So this is k dot equal to 1, right? Now I do I transform in Fourier space. As I told you many times, the idea of the Fourier transforms is to transform a differential equation into an algebraical equation, and this is exactly what happens here, because the Fourier transform of the D'Alembertian is just k dot k, right? Then here you put the d tilde, and the Fourier transform of the delta function, you can read it off from here, it's just 1. So you see immediately you have the solution, at least in Fourier space, that is 1 minus k squared. And exactly as we had, so this is no big deal. But now, as usual with this Fourier business, what is a little bit tricky is to come back into ordinary space from the K space, because now you have to write what is your solution. I mean, your green function is going to be this dz that is going to be, so you get 2 pi to the 4th minus, because you have a minus there, and then you have to do this integral. And so I have to do this integral, but you see that there is a singularity in the integral, so it's not, you cannot do it right away. You have to be a little bit careful. And the singularity is where? So if you, so this is an integral. You may, let's do it. If you draw the k naught part of the integral, right? You see that here this is k naught square minus k vector square, right? And you see that you have singularity where this thing is equal to 0, right? So this quantity, you can call it kappa square. So let's call kappa the value, the modulus of the vector k. So you see that you have two poles, one here and one here. Okay, so a plus the absolute value of the space part of the vector k, and the same on minus k. So if this is the when you do the, so here you have dk naught times d3k. So when you do the integration over k naught, you hit these two poles. Okay. So this integral is minus 1 over 2 pi 4 to the 4th. Then you have the three-dimensional integration, z. And then you have this singular integral that goes from minus infinity to plus infinity of the k naught of minus so I guess right. So this is this. I wrote down explicitly that integral. So you see this is okay. Then you have to do this k naught integration, and so this is the integration in k naught. You see you have two poles. So you have to give a prescription about these poles, right? And so you have a contour here to do this integral. So you go to a complex space of the k naught parameter. That's the way you do this integral. You see you can have a contour like this. And also you can have a contour down here. And depending on which one you pick, what do? You close this path, right, up here or down here. That is for z0 less than 0. For z0 less than 0, you close it up here. Otherwise, you have to pick the other contour. And you see, this is the usual thing that you take it large enough in such a way to that gives no contribution, right? And therefore, the contribution of this integration path. So let's take this. Let's take this the one the lower one, okay? It's just the sum of the residues inside this path, right? You remember this from your from Narayan class. So this integral here, I write it as an integral over that circuit over dk naught, right, of e minus I k naught 0, k naught minus k squared. This is the sum, so minus 2 pi I, the residues of these things. But you see that the residues of this in the two poles is what? Is one time e to the minus and the other time e to the plus. So it's essentially is the sign, right? You remember this is the sign of kappa z naught. You remember that the sign of z is e to the iz minus e2, so you get this. So the entire integral by using, and you see I took this path here, so I took z not always larger than 0, so I get outside a theta function for z naught divided by 2 pi to the cube, because a 2 pi gets absorbed here. The I, I'm sorry, 2 pi, yes. No, sorry, here it's 2 pi, sorry, so this is the sum of the residues. So when you do that, you get minus 2 pi, because the I goes in the definition of the sign, then you have a 1 over k sine of k z naught. So here, I finally get the integral over the d3k, the vector part, that I still have to do, this one, e to the ikz, now three-dimensional things, times this sine of kappa z naught over kappa. Very good. So I'm almost there. Actually, you can do part of this integral, you can do it right away. And you know, this function is the one that is 0 if the variable is negative and 1 if it's positive, right? Is the theta function, is the step function, right? So you can do the angular part of this integral, and the result is that you kill a few factor of pi and 2. Then you brings down. You see, this is you bring down the z, 1z, and you are left with the sign again. So this, so kappa is the absolute value of k. In fact, let's call now big R the absolute value of z, because it will pop out. So let's call it R. So that's the result of the integration. You see, I've integrated everything except the length of k that I still have to do. But even that integration is not very complicated, because by using trigonometry, you can replace these signs by the sum, right? Each of them is I, you see, you can combine them. You write the sign as e to the I k r minus e to the I minus kr. Then you multiply the two, and you get this. Right? And then it's easy to integrate these things, right? Because for this bound, this gives no contribution, and this gives you just a delta function. So the end of the story is just you get this theta z0 over, so actually this, there is a pi, right? This is a one-dimensional, so this is pi over 2, the delta function of z0 minus r, r. Okay, so my r looks a bit like a... So when you plug in here, you get 2 pi, 4 pi because of 2, 4 pi big R, and then just a delta function, right? This z0 minus r. So this was a sort of long computation, but the end result is very simple, because then you have that your delta, your green function, okay, so let's put back z was the difference between the points. So your green function is theta x naught minus x prime naught, right? If I substitute for z the original value, divide by this 4 pi r, where r is the measure of the distance in space, and here you have x0 minus x prime 0 minus r. So very compact result. This is the green function for this equation, and is called the retarded. You remember these things about the retarded advance, and this was because I took this path here, right? I took this one, so this is the retard. If I had taken the other one, that is a good solution as well. This is the advanced one. But you see, the advanced one it's called advanced because you see here I was integrating for z naught greater than 0, right? So z, this is x minus x prime greater than 0. So you see, this is for things that happen afterward. So that's why it's called retarded. So you determine what is happening from what happened before in the light cone before the, right? So in space-time, if you are here, you determine this is the light cone of this point. So this is what happened here determined the fields in this point. This is the retarded solution. Because of the invariance between time inversion, you could have a good solution also if you use the advanced one, in which you take everything that happened here, you run it backward in time, and you determine the solution here. But because of the way our brain works, that we have causality from the past, right, not from the future, you always take the retarded solution. But mathematically, as we already discussed, you could have taken, in fact, even half and half. You can take half retarded and half advanced, and that would be a good solution as well. But let's stick to the retarded, so this is the green function. And because I have the green function, I can write the solution. So the solution, the A alpha, let me call it, or A beta, is going to be what? It's going to be a generic solution, right, of the homogeneous equation, the one in which you put 0 here. So whatever is there before you introduce the sources, maybe an electromagnetic wave passing by, plus the particular integral of this inhomogeneous equation that I write in terms of the so 4 pi c, the integral over d4x prime, the retarded green function. So this let's call it r, the retarded, x minus x prime g alpha in x prime So that's the generic solution of the Maxwell equations, now written in a manifestly covariant form in space-time. So you see, it's a little simpler to work in directly in space-time if you compare to what we did when we solved the Maxwell equation in general in three-dimensional space. At least it seems simpler to me. But okay. Questions? So this is really all there is, but we can specify some solutions, right? If we, so this is for a generic charge and current distribution. So as usual, we can go to our favorite case, that is the single charge moving around the space-time. So what is J alpha for a single charge? Is something, so give a charge, say an electron or charge E. There is always this C around that I'm not very then you have to integrate over the path of this particle, you remember? So what is the charge density? You integrate the velocity, that is a forward velocity of your particle, okay, over the path of this particle. And so this integral has a delta function x over the position. So r of tau is the trajectory of your particle. So you put a delta function. So you put this x to be the x. So if this is the r of tau, x is here. So you put a delta function in order to identify that point, and you multiply the charge by the forward velocity. Okay. So this r is a vector with component, say ct. So let's take c equal to 1, r of t, right? Is the trajectory of the particle, but written in space-time. There is a c here, but I'm taking c equal to 1 to avoid. Yes. I mean, there should be a c here, and then also you have a. Well, of course, here you have c. So, okay, but I'm taking c equal to 1 to avoid too much editing in the final result. So, okay. So you see that if you plug, so you have your delta function right here. Now I plug this j in here, and I can write the A alpha, the solution. Let's take that you don't have any incoming 4 vectors, so you just have your sources, so you don't have the solution of the homogeneous equation, so you only have this. So if you take this, you plug in there, you see there are factors, now c is equal to 1, 4 pi. I think if I did it correct, you get the 2e. Then you have this integral over the proper time of the particle, u alpha tau. This is just goes across. Then you see you have this series of, well, you have the theta function, of course, this x minus x prime naught. But you see you have also this delta, so you have this delta function and this delta function. They play together, so that here you should replace, because of that of this delta function and the interplay there. You see x goes in there, so you get x naught at certain. I'll tell you in a second what this is. And then you have the three-dimensional things. Square. So what is this? You see, you have this constraint. So you see, if this is time and this is space, and you have your trajectory, as I said, right? And you are in point x here. So here's the charge moving, and here you have your x point. You see, this is it's a cone. It's a Lie cone, right? Because this is the Lie cone for this point x from here to there. So you get that the only contribution to the A alpha field in here is the one produced by the particle at the retarded time, of course, when the particle was here. So this is r tau naught, say. This is the trajectory r tau. Okay? That's exactly what we already knew from the previous computation, that the field here is not, you see, this is the time t, but it's not generated by here, but by the retarded position of the particle when it was here, such that the influence or the generation of this field runs along this light-like propagation at the speed of light. So there is only this, okay. And actually, you see, you can even do this integral, right? If you remember the property of the delta function, right? And if you do that, you get the final result. That is, so you have the charge, the velocity there, and then u dot x minus r tau at the retarded time, if you do this integral. And so this is the four-dimensional form of the Leonard, how do you write it? Potentials. And you can see that they go in what we computed in a three-dimensional space. If you well, it requires a little bit of, so you see, for instance, let's look at the zero components, right? You see, this distance here, this u dot x minus r of tau, this is u naught x naught minus r of tau naught tau, right? Minus the vector part. And you see, you remember that u alpha is equal to, well, it is equal to gamma c, so 1, or if you want to put back c and v, right? So if you do that, you see that this is equal to gamma. Let's call the let's call R, big R, as I did before, the distance between x and R at this time tau. This is on the light cone, so this is exactly equal to x naught minus R naught. So if I use this big R, this is gamma R, there is a C, but let's put it equal to 1, minus gamma V n R, where n is the vector, as usual, that points from the position of the particle to where you are computing the field. So if you put this inside here, you see that the zero component of this, that is what you call the scalar potential of the linear Vickers potential. So I take the zero component of this. So this is the zero component. So it's just this gamma C. Then the gamma simplifies, and I get just the charge divided by what? You collect this. You see 1 minus this V. There is this C, so it's a beta really, right? N, and you collect at the retarded time. And this, if you remember, is what we derive for the linear Vickers potential for the case in a three-dimensional space. And similarly, you can write exactly the same things if you put the beta here, right? I think it's exactly the same. This is the vector potential. So you see, it's much more compact and I think simpler in a way, or maybe not. I don't know. It's more difficult. But it was not easy even in 3 dimensions, I think. So, well, at least here is all well. Anyway. So what else? Well, of course, you can compute directly from here the fields, the field strengths, the F alpha beta, but okay, I think we are running out of energy. So maybe the last thing one wants to so let me skip these other parts because I see that we are tired. It's Friday. So what else I wanted to say? Just maybe just the final words about the emitted power, right? When this electron is accelerating, is you remember the Larmor formula? Do you? What is it? Okay, that's pretty good. Yeah. So we derive this formula that for a charge accelerating, right, the power emitted by electromagnetic radiation was E squared chi, so C equal 1, but now I have it, and the acceleration, right, square. Then if it was moving with the with the periodically you would get this the law. So what is the in a way you can immediately generalize this to the relativistic limit. I mean the covariant generalization of this. Because it has some features that are not there in the formula that we derived. That was a non-relativistic. So this is good if the electron is moving with speeds much less than c. What happens if this electron starts moving on a speed that is comparable? Well, you have to generalize this to the, and it's the usual thing. You have here divide and multiply by m. So then you see, this becomes a p, right? So you can take, so you have 2/3 e square m square c to the cube, and then you have a dp mu d tau dp mu d tau. That is the generalization of this time derivative. So I replace the time derivative with derivative with respect to the proper time. And depending on the signature, you put a minus here or you don't put a minus there, depending on the fact that you have that p square is minus or plus. Okay, the signature of your. So you see, it becomes a little more complicated because you have two components here, because you have the vector part, right? The vector part, that is this, and then you have the time part. Or, to write it in a nicer way, so if you expand this expression here, let's write it here, I think you get this, you see, because E is equal to gamma mc square, right? And P is equal to gamma mv. So if you replace there, you get, you collect a bunch of gammas from there and there, and the final result is this one. So let me just write the final. This is a result, so this is the power emitted by an electron moving with arbitrary velocity. This was derived by Leonard, the same of the potential, without Vickers. That they didn't work together. I mean, one was German, the other French. And they just got the potentials at the same time. But then he derived this, so this is the generalization of the Larmor formula when the particle, you see, is moving at speeds comparable to the velocity of the. Okay. Now you can then compute the electric field and the magnetic field, and then the Poynting vector. So I'm not going to do it because, well, you find it in your textbook. And the only thing I want to say, so this is the power emitted. How is this power emitted? You remember that it has a characteristic angular distribution. And this characteristic angular distribution is given by this formula. So what I'm skipping here is to write the electric field from our potential, and then from the electric field you keep the radiation part, and then you write the Poynting vector. If you do that, you see that the power, the angular distribution of the power emitted, this is the total power, right? This is, you see, is the angular distribution of this emitted, has this form here. I just write the result so that we don't. This is the norm, the unit vector between the, so this electron is moving in this direction, okay, and this n is pointing where you are looking. So if this some angle theta, okay, and so is something like this. Beta is v over c square 1 minus n dot b to the fifth. So what is interesting is that if you introduce this angle, you see that you have this angular here you have 1 minus beta cosine of theta, right? And down upstairs you get the sine theta square, right, because of this. So in other words, it has an interesting distribution, right? That depending on the value of beta, you remember that for small velocities, we discovered that the radiation was all emitted in this direction here, right? But now you see that if beta becomes, so this was for beta close to 0, for v much less. But for beta coming close to the speed of light, beta close to 1, these two goes down. They go like this. So they tend to close toward the direction of the motion of your electron. So this is the synchrotron radiation of this electron, and it tends to come close to the direction of motion as you come close to the speed of light. Okay? Yes?
You say that as it comes closer to the speed of light, it becomes like a wall.
Well, close to 1 is very close to this direction. So if it goes very slowly, you don't have radiation in the same direction of the motion. On the other direction, it comes closer. So for instance, CERN, they accelerate, you have a lot of synchrotron radiation along the pipeline.